Amplifier circuit using FET and MOSFET. All the formulas are same whether it is designed using FET or MOSFET. Common source configuration, voltage gain AV equal to V0 by Vi, that equal to numerator part minus mu RD, denominator part small RD plus capital RD plus 1 plus mu into RS. Small RD plus capital RD plus even is separate to 1 plus mu into RS is separate to, that is the denominator part. So whole equation equal to minus mu RD by RD plus 1 plus mu RS. If RD small RD tends to infinite, then AV equal to minus GM capital RD, that is the numerator part, by 1 plus GM RS. GM RS another one part to one another separate. So AV equal to minus GM RD by 1 plus GM RS. If RS equal to 0, then AV equal to minus GM RD, where AV means voltage. Input impedance Zin equal to R1 parallel to R2. Output impedance Z0 with load RD equal to capital RD parallel of RD plus mu plus 1 into RS. Without load RD, capital RD, Z0 equal to small RD plus mu plus 1 into RS. Mu plus 1 into RS in the part. If RD tends to infinity, then Z0 equal to RD, where RD means drain resistance. RD means drain resistance. Common drain amplifier. Voltage gain AV equal to mu RS numerator part, denominator part RD plus mu plus 1 into RS, that equal to V0 by Vi. If small RD tends to infinite, then AV equal to GMRS, that is the numerator part, by 1 plus GMRS, that is the denominator part. Output impedance without load RS equal to RS, Z equal to numerator part small RD plus capital RD, denominator part mu plus 1, where capital RD is the drain resistance, RS is the source resistance, R1 R2 is the pike R1 kinda R2. If RD tends to infinity, then Z equal to 1 by GM. Output impedance with load RS, Z0 equal to numerator part RD plus small RD plus capital RD, denominator part mu plus 1, parallel with RS. If RD tends to infinity, then Z0 equal to 1 by GM parallel with RS. Common gate amplifier. Unloaded voltage gain AV equal to GMRD. Input impedance Zin equal to 1 by GM parallel with RS. Output impedance Z0 equal to capital RD. DC on state resistance RDS on equal to VDS by ID, where RDS on equal to DC resistance in saturation region. VDS means DC drain source voltage. ID means DC drain current. Common source amplifier is equivalent to CE amplifier of BJT. Common drain amplifier is equivalent to common collector of BJT. Common gate amplifier is equivalent to common base amplifier BJT. Common drain amplifier is also known as source follower. Common gate amplifier has unity current gain, low input resistances, high output resistances, and high voltage gain. Low frequency analysis of FET amplifiers. Small signal low frequency equivalent of JFET. GM VGS RD both are parallel. Amplifier are analyzed at low frequency by considering the effect of large capacitance like CBCC. Low frequency analysis of CS amplifier is same as of low frequency analysis of CE amplifier. Modulus of AVL equal to modulus of AVM whole by root of 1 plus FL by F whole square. FL by F1 is separate to whole square. Numerator part is AVM, numerator part is root of 1 plus FL by F whole square. Angle of AVL equal to 180 degrees plus tan inverse of FL by F. If CC is considered, FL equal to 1 numerator part, denominator part 2 pi CC RD dash plus RL. If bypass capacitor CS is considered, FL equal to GM, that is GM is the numerator part 2 pi CS. If CB is considered, FL equal to 1 numerator part 2 pi CB into RS plus RI dash. High frequency analysis of FET amplifier. It is performed by considering the effect of small capacitor. Small capacitor means external shunt, C shunt, internal FET capacitance, CGS, CGD, CGD, transition capacitance, gate channel junction. CDS means internal capacitance of channel. Small signal high frequency equivalent of FET amplifier. In common source configuration, CGD will be present between input nodes, gate and output node drain. Therefore, it can be replaced with CM and CN using Miller's theorem. CM equal to CGD into 1 minus AV. CN equal to CGD into 1 minus 1 by AV. 1 by AV and separate to 1 minus separate to, then modulo minus. CN appear in parallel with CGS. Therefore, net capacitance between gate and source or net input capacitance will be CI equal to CGS plus CM. CI equal to CGS plus CGD into 1 minus AV. CN appears parallel to CDS. Therefore, net output capacitance will be C0 equal to CDS plus CN. C0 equal to CDS plus CGD. Miller effect occurs in CE and CS configuration. It causes increase in input capacitance. HF analysis of CS amplifier is same as that of CE amplifier. Modulus of AVH equal to numerator part modulus of AVM denominator part root of 1 plus f by fh whole square. F by fh plus 1 and separate. The angle of AVH equal to 180 degrees minus tan inverse of f by fh. If CHS is considered, FHH equal to 1 by 1 numerator part 2 pi RL hash CHH. If CA is considered, FH equal to 1 numerator part 2 pi CA into RDS parallel with RS, where RL dash equal to RD parallel with RL and RL double dash equal to RL dash parallel to RDS. Analysis of large signal amplifier. Load line analysis for common emitter amplifier where ICQ equal to quiescent collector current, VCEQ means quiescent collector emitter voltage, Thevenin resistance driving base, RB equal to RS parallel with R1 parallel with R2, AC load resistance seen by collector, RC equal to capital RC parallel with RL. Equation of AC load line: IC equal to ICQ plus VCEQ by AC, VCEQ by RC minus VCEQ by RC. No. Again, I will see. Equation of AC load line: IC equal to ICQ plus VCEQ by RC minus VCE by RC, where ICQ tends to DC collector current, VCEQ tends to DC collector emitter voltage, small RC means AC resistance seen by collector, AC saturation current IC sat equal to ICQ plus VCEQ by RC. VCEQ by RC is separate, ICQ is separate. When the transistor goes into saturation, VCE equal to 0, AC cutoff voltage VCA cut equal to VCEQ plus ICQ RC. AC output compliance of a CE amplifier PP equal to minimum of T 2 into ICQ RC, 2 VCEQ. AC output compliance is the maximum unclipped peak to peak AC voltage that an amplifier can produce. For emitter follower amplifier, effective AC load resistance small re equal to capital RE parallel with RL. AC saturation current IC sat equal to ICQ plus numerator part VCQ by RE. VCQ by RE is separate. AC cutoff voltage VCE of cutoff equal to VCQ plus ICQ RE. AC output compliance of an emitter follower PP equal to minimum of 2 ICQ RE, 2 VCE. For common base amplifier, AC load resistance of CB amplifier RC equal to RC parallel with RL. Small RC equal to capital RC parallel with RL. AC load line and AC output compliance of CB amplifier is same as the of CE amplifier. For swamped amplifier, AC saturation level IC sat equal to ICQ plus ICQ separate to numerator part VCQ, denominator part RC plus RE. AC cutoff voltage VC cutoff equal to VCEQ plus ICQ into RC plus RE. AC output compliance of a swamped amplifier PP minimum of 2 ICQ VRC, 2 VCQ into RC, that is the numerator part, denominator part RC plus RE. For maximum AC output compliance, ICQ RC equal to VCQ CE voltage stage, ICQ RE equal to VCQ CC, ICQ RC equal to VCQ RC whole by RC plus RE swamped. Next, power amplifiers. Very important topic. Power amplifiers. It is a lower signal amplifier which has greater AC output voltage and greater AC output current, hence it can provide greater AC output power to load. Conversion efficiency is the ability of power amplifier to convert DC power into AC power. Eta equal to PAC by PDC into 100%. Harmonic distortion. The harmonic distortion means the presence of the frequency components in the waveform which are not present in the input signal. IC equal to B0 plus B1 into cos omega t plus B2 into cos 2 omega t plus and so on. Bn cos and omega t. IC equal to B0 plus B1 cos omega t plus B2 cos 2 omega t plus and so on. Bn cos and omega t. Percentage of Dn equal to modulus of Bn by modulus of B1 into 100%, where n equal to 1, 2, 3 and so on. Here fundamental frequency component has the amplitude B1 and nth harmonic component has an amplitude of Bn. Thus total harmonic distortion percentage D equal to root of D2 square plus D3 square plus D4 square and so on Dn square into 100%. Classification of power amplifiers. Class A operation. Transistor operates in active region at all times. Collector current flows for 360 degrees of the AC cycle. Unloaded voltage gain of CE amplifier A equal to minus RC by RE dash. Loaded voltage gain AV equal to minus RC by RE dash. Current gain of the transistor AI equal to IC by IB, where AI equal to current gain, IC equal to AC collector current, IB equal to AC base current. AI equal to beta. In most of the circuits, this approximation can be used. Power gain AP equal to minus AV into AI. load power PL equal VL square by RL equal to VPP square by 8 RL. PL means AC load power, VL means RMS load voltage, VPP means peak to peak load voltage, RMS means load resistance. Transistor power dissipation, PDQ equal VCEQ into ICQ, where PDQ means quiescent power dissipation, VCEQ means quiescent collector emitter voltage, ICQ quiescent collector current. Total DC power supplied to an amplifier PC equal VCC into IS. Maximum AC load power PL of max equal PP square by 8 RL, where PP means maximum unclipped value of VPP. Stage efficiency eta equal to PL max by PS into 100%, where eta means stage efficiency, PS means DC input power. Class A amplifier produces least distortion in output among all power amplifiers. The maximum efficiency of Class A amplifier is 25%. Class B operation. Collector current flows for only 180 degrees of the AC cycle. U point is located approximately at cutoff on both the DC and AC load lines. Collector emitter voltage at Q point VCEQ equal to VCC by 2. AC load power of a Class B push-pull amplifier PL equal to VPP square by 8 RL. Output signal is half sinusoidal. Quiescent power dissipation of power drain is almost zero. The maximum efficiency of Class B amplifier is 78.5%. Class AB operation. Operating point is located between the limits of Class A and Class B. Collector current flows for more than half sinusoidal but not fully sinusoidal. Distortion in Class AB amplifier is more than Class A but less than Class B. Power drain is more than Class B but less than Class A. Class C operation. Class C operation, it is operated either in deep saturation or in deep cutoff region. The collector current flows for less than 90 degrees of the AC cycle. Tuned amplifier. Tuned amplifier means LC, VCC, RL, RB. Resonant frequency of tank circuit FR equal to 1 by 2 pi root LC, where L means inductance, C means capacitance. AC load power Class C amplifier PL equal to VPP square by 8 RL. Remember, it has highest conversion efficiency among all power amplifiers. Class C output is a heavily distorted. It is used in tuned power amplifiers and radio frequency amplifiers. It has highest conversion efficiency among all power amplifiers. The maximum efficiency of Class C amplifier is 87.5%. Class A power amplifier, conduction angle is 360 degrees, maximum efficiency is 50%, figure of merit is 2. Class B power amplifier, conduction angle is 180 degrees, maximum efficiency is 78.5%, figure of merit is 0.4. Class AB power amplifier, conduction angle is 180 degrees, 360 degrees, maximum efficiency is 50 to 78.5%, figure of merit is 0.4 to 2. Class C power amplifier, conduction angle is less than 180 degrees, maximum efficiency is greater than or equal to 90 degrees, figure of merit is less than 0.25. Feedback amplifiers, basic feedback concept. Source SI sigma, source SI వస్తుంది, feedback negative వస్తుంది. SE A beta is the feedback factor, S naught then gives load. A means open loop gain, beta means feedback factor, SI means input signal, SE means error signal, SF means feedback signal. Gain with feedback, AF equal to A by 1 plus A beta for negative feedback, AF equal to 1 by A minus beta for positive feedback. The amount of feedback introduced into amplifier is often expressed in dB and is given by N feedback in dB 20 log of numerator part 1, denominator 1 plus A beta. 20 log of 1 by 1 plus A beta, that is modulus. 20 log of modulus 1 by 1 plus A beta. N means negative for negative feedback and N means positive for positive feedback. Loop gain or return ratio, loop gain equal to minus A beta. Return difference between unity and loop gain is called return difference D equal to 1 plus A beta. D is also called a desensitivity. Insensitivity in the case of negative feedback, if dou A by O is equal to percentage change without feedback, dou AF by dou AF by AF, percentage change with feedback. Reduction in sensitivity of amplifier, dou AF by AF equal to dou A by A whole by 1 plus A beta. 1 plus A beta. Feedback amplifier. Feedback amplifier, source, mixer, basic amplifier, sampler, feedback amplifier. Sample circuit, voltage shunt amplifier, shunt sampler. వోల్టేజ్ షంట్ శాంప్లర్లో ఏమొస్తుందంటే అవుట్పుట్ షంట్ తీసుకుంటాం, బీటా తీసుకుంటాం, ఇన్పుట్ తీసుకుంటాం. ఓకేనా. నెక్స్ట్ సెకండ్ వన్ శాంపుల్ సర్క్యూట్లో సెకండ్ వన్ కరెంట్ ఆ సిరీస్ శాంప్లర్. కరెంట్ ఆ సిరీస్ శాంప్లర్లో బేసిక్ యాంప్లిఫైర్ డైరెక్ట్ అవుట్పుట్ సిరీస్ విత్ ఆర్ఎల్ ఐ నాట్ బీటా. Mixer, series or voltage mixer comparator. Input is given series directly to beta. Shunt or current mixer comparator. Input of current source is given directly shunt to beta. Next, effect of feedback. Reduction in noise, N naught of F equal to N naught by 1 plus A beta, where N naught means noise without feedback, N naught of F means noise with feedback. Lower cutoff frequency, FILF equal to FL by 1 plus A beta. When FLF is lower 3 dB frequency with feedback, FL means lower 3 dB frequency without feedback. Upper cutoff frequency FHF equal to FH into 1 plus A beta, where FHF equal to tends to upper 3 dB frequency with feedback. FH means upper 3 dB frequency without feedback. Bandwidth increases with negative feedback. Voltage series topology. voltage amplifier దానికి వోల్టేజ్ సిరీస్లో వోల్టేజ్ యాంప్లిఫైర్ అనేది డబ్బాకి దాని యొక్క ఇన్పుట్ అనేది బీటా ఇస్తాం, దాని యొక్క షంట్ అనేది బీటా ఇస్తాం. వన్స్ అగైన్ వోల్టేజ్ సిరీస్ టోపాలజీ. వోల్టేజ్ యాంప్లిఫైర్ అవుట్పుట్ ఈస్ గివెన్ షంట్ టు బీటా, input is given as series VF, beta is dimensionless, voltage series feedback stabilizes the voltage gain. Example, common character non-inverting amplifier. Current series topology. Transconductance amplifier, input is given as series to beta and output is given as series to beta, that is called as current series topology. Unit of beta is ohms. Current series feedback stabilizes the transconductance gains. Example, common emitter. Voltage shunt topology. For transresistance amplifier, the output is given to as beta as shunt and input also given as shunt. Beta has unit mho. It stabilizes the transresistance gain of the amplifier. Example, collector to base biasing. Current shunt topology. Current amplifier, output of series is given to beta series and input is shunt is given to beta. Beta has no unit, it stabilizes the current gain of amplifier. Example, cascading amplifier. For different feedback configuration, effect on input and output impedance and gain. Once again, voltage shunt topology. Transresistance amplifier, output is shunt, input is shunt. Current shunt topology. Current amplifier, output is series, input is shunt. Beta has no unit, it stabilizes the current gain of amplifier. Example, cascading amplifier. For different feedback configuration, effect on input and output impedance and gain. Feedback, voltage series feedback, input voltage, output voltage, gain is AV, RI increases, R0 decreases. Current series feedback, input is voltage, output is current, gain is denoted as GM, input resistance RI increases and R0 also increases. Voltage shunt, current is input, output is voltage, gain is RM, so RI decreases, R0 decreases. Current shunt feedback, input is current, output is also current, gain is equal to AI, RI decreases, R0 increases. Voltage series feedback is the best arrangement in terms of RI and R0. Current shunt is the worst for the same. Voltage series feedback is the best arrangement in terms of RI and R0. Current shunt is the worst for the same. Remember, procedure to identify the type of feedback. Identify the element responsible for the feedback. If feedback element is directly connected to the output node, it indicates voltage sampling, otherwise it indicates current sampling. If feedback element is directly connected to the input node, it indicates shunt mixing, otherwise it indicates series mixing. Operation amplifier, differential amplifier. Vout equal to A times of V1 minus V2. Two common emitter resistance దగ్గర కామన్గా RE పైన RC VCC వస్తుంది. VOT means voltage between collectors. A means capital RC by small RE equal GMRC. ఓకేనా. RE tends to emitter resistance. V1 means non-inverting input voltage. V2 means inverting input voltage. DC analysis of a differential amplifier. VCC, Q1, Q2, VE, RB. Emitter bias IE equal to VE minus VBE by 2RE. VE minus VBE numerator part, 2RE is the denominator part. Tail current IT equal to VE minus VBE numerator part RG. AC analysis of a differential amplifier. non-inverting input, AC emitter current IE equal to V1 by 2RE, where RE means emitter resistance. AC output voltage V out equal to ICRC equal to V1 RC whole by 2RE. Voltage gain for non-inverting input V out V by V1 equal to RC by 2RE. Inverting input AC emitter current IE equal to V2 by 2RE. AC output voltage V out equal to minus ICRC, that equal to minus V2 RC by 2RE. Voltage gain for non-inverting input V out by V2 equal to RC by 2RE. Differential voltage gain A equal to RC by 2RE. Input impedance Rn equal to 2 beta Re. Common mode voltage gain ACM by VNCM equal to minus RC by numerator part is RC minus RC, denominator part is RE plus 2RE, small re plus capital 2RE, minus RC by 2RE, capital RE far greater than RE. CMRR equal to modulus of A by modulus of CM, where A means differential mode gain, ACM is common mode gain. CMRR equal to differential mode gain by common mode gain, that equal to 2GMRE. Operation amplifier in op-amp is basically a very high gain direct coupled amplifier with high input impedance and low output impedance. Non-inverting input, inverting input, input stage, intermediate stage, level shifting stage, output stage, output. Equivalent circuitry of op-amp. Op-amp amplifies the between the two input signals applied at non-inverting and inverting input terminals. V2, V1, R1, VCC, AVD, R0, V0 equal to AVD, where difference input voltage tends to VD equal to V1 minus V2. A means open loop gain of op-amp. Output voltage V0 equal to AVD. Ri means differential input resistance. R0 means output resistance. Properties of op-amp. Parameters: voltage gain ideal value infinite, practical value 10 power 6. Input resistance ideal value is infinite, input resistance practical value is 10 power 6 to 1 mega ohms. Output resistance ideal value is 0. Practical value of output resistance is 10 ohms to 100 ohms. Bandwidth of ideal value is infinite. Bandwidth of practical value is 10 power 6 H2 or 1 megahertz. CMRR ideal value is infinite. CMRR practical value is 10 power 6 or 120 dB. Slew rate ideal value is infinite. Slew rate practical value is 180 volts per microsecond. Slew rate condition for distortionless output: SR greater than or equal to numerator part 2 pi f Vm ACL, denominator part 10 power 6. SR must be greater than or equal to 2 pi f Vm ACL by 10 power 6. For input Vm sin omega t, f max equal to slew rate by 2 pi ACL Vm. 2 pi ACL Vm is the denominator part, where SR means slew rate, f max means maximum frequency of operation, ACL means closed loop gain of op-amp. Bias currents and voltage. V0 is not equal to 0 called output offset. Balanced condition: IB1 IB2 రెండు ఇన్పుట్ కి ఒక వోల్టేజ్ సోర్స్ ప్లస్ కి ఒకటి పవర్ సోర్స్ మైనస్ కి ఒక సేమ్ ఉండి గ్రౌండ్ అవుతుంది. దట్ ఈస్ కాల్డ్ బ్యాలెన్స్డ్ కండిషన్. ఇన్పుట్ బయాస్ కండిషన్ IB ఈక్వల్ టు IB1 ప్లస్ IB2 హోల్ బై 2. ఇన్పుట్ offset current II0 equal to IB1 minus IB2. Input offset voltage is the voltage which must be applied between input terminals to balance amplifier. That means V0 equal to 0. Linear op-amp circuits. Inverting amplifier. VI means VI RF VO0. Gain equal to AV equal to V0 by VI equal to minus RF by R1. Numerator part, denominator part 1 plus RF by R1 by ANOL. How can we realize minus RF by R1 whole by 1 plus RF by R1 by AOL. 1 plus R by అది కూడా న్యూమరేటరే, కానీ న్యూమరేటర్ కింద డినామినేటర్, బట్ డినామినేటర్ కింద న్యూమరేటర్ బై AOL, వేర్ AOL మీన్స్ ఓపెన్ లూప్ గెయిన్ ఆఫ్ ఆప్ యాంప్. ఐడియల్లీ AOL ఈక్వల్ టు ఇన్ఫైనైట్. AV ఈక్వల్ టు minus RF by R1.